This video will introduce you to carbohydrates, one of the 4 biological macromolecules. By the end of this video, you should be able to name linear sugar molecules, determine their configuration, and determine the relationship between sugars. Just as amino acids make up proteins and nucleic acids make up DNA, single sugar molecules called monosaccharides make up carbohydrates. First, we'll cover what carbohydrates are, then how to name them, followed by determining their absolute and relative configuration. Carbohydrates are organic molecules made up of carbon and water, hence the name carbo and hydrate. They have the molecular formula CxH2O(Y). For example, glucose has the molecular formula C6H2O6. You've probably seen it as C6H12O6. Monosaccharides can exist as linear molecules or rings. While it's more accurate to use the word monosaccharide to refer to a single sugar molecule, we often just say sugar. Looking at a linear molecule, one carbon will either have an aldehyde or a ketone. This gives us the prefix aldo or keto. The total number of carbons in the molecule are incorporated into the name as well. Pent for 5, hex for 6, and hept for 7. Sugars of 4 carbons can exist too, but we commonly see 5 and 6 carbon sugars in biological processes. Finally, the suffix -ose is added to indicate that it is a sugar. This molecule is a ketohexose because it is a 6-carbon sugar containing a ketone. The specific ketohexose is called fructose. What would you call this molecule? This is an aldopentose, a 5-carbon sugar with an aldehyde. This specific aldopentose is ribose, the sugar component of nucleic acids. An important aspect of monosaccharides, like amino acids, is their chirality. Monosaccharides contain several chiral centers. In Organic Chemistry 1, you learn about R and S absolute configuration of chiral centers. We can determine the absolute configuration of all of the chiral centers in sugars by using the Fisher projections. The atoms branching off from the carbon chain are on wedges. Glucose is an aldohexose and its chiral centers have R, S, R, and R configurations. We can describe sugars as a whole with the L and D configuration instead, which is called the relative configuration. To determine if a molecule is L or D, we look at the chiral center furthest away from the carbonyl. If the OH on that bottom carbon points to the right, it is D. Looking at glucose again, the last chiral center has the hydroxyl pointing to the right, so it is D-glucose. If the hydroxyl points to the left, it is L. Sugars can be either L or D, but in nature they almost always exist in the D form. We use the L and D relative configuration to describe amino acids too, which are typically L in nature. Now that we've seen the absolute and relative configuration of glucose, what happens if we change some of these chiral centers? If we change all of the chiral centers in glucose, we get its enantiomer, which is L-glucose. If we change at least one, but not all chiral centers, we get diastereomers of glucose, which are completely different monosaccharides. For example, if we change the configuration of the second carbon in D-glucose, we get D-mannose. If instead we change the 4th carbon in D-glucose, we get D-galactose. The relationship between glucose and mannose, and glucose and galactose, are a more specific type of diastereomers, called epimers. Epimers are produced when just one chiral center changes. D-galactose and D-mannose are diastereomers, because more than one, but not all chiral centers have changed. In a future video, we will cover how these linear molecules cyclize. In summary, carbohydrates have the formula CxH2O(Y) and are typically written in these Fisher projections. The chirality of sugars is important, and changing a combination of chiral centers produces different sugars that can be epimers or diastereomers of one another. The most common sugars we see in biochemistry are glucose, galactose, fructose, mannose, and ribose, all of which differ in their stereochemistry, whether it's a ketone or aldehyde, and the number of carbons.